Going great with Go. Building a SQL helper in Go with Ayan George.
So, my name is Ayan George. I live in Maitland, Florida. I'm CTO of a small startup in Central Florida. We're going to change how people do e-commerce. I've been using Go for a few years now. My background is in C. I've been using C for many years, and transitioned to Go maybe about 4 years ago. And so one of the things that struck me about Go is it's a compiled language, statically typed, but it provides a really rich standard library and allows for really powerful abstraction techniques. So what I want to do is go over some of those things. Let me get my slide deck up. And I'm already having trouble. Let's see. I don't see, oh, there we go. Share screen. Application window. Great. So can everyone see that? Is the font okay?
Yep. Yep.
Okay, so this is how I'm going to talk, Reflections on Database Access in Go, and kind of subtitles, Leveraging Go's standard library. Hi. Today, I'd like to briefly discuss some of Go's interesting features. Unfortunately, I don't have enough time to dive as deeply as I'd like to. I'm feeling a lot of time pressure. This is as meta as I'm going to get, but I am feeling a lot of time pressure. I only have 30 minutes. And Go is a really fascinating language, and I could go on for hours. I see some of my local meetup members here, and as they can tell you, I can go on for hours about some of this stuff. So what I hope to get out of this talk is that if you're new to Go, you'll walk away with a deeper interest in it. If you already understand, if you already use Go, I hope there's one or two things, one or two insights that you'll get from this. I also feel like I'm not doing Go. I'm kind of doing Go a disservice by not talking about concurrency. Unfortunately, that's not part of my talk today. But that's definitely one of the major features of Go, and so definitely look into that after the talk. Also giving this talk in part to solidify my understanding of these concepts. Sometimes it helps to talk about things or kind of force you to give talks in order to fully understand some topics. And so if there's anything, if you have any criticisms or critiques, or if I get anything wrong, you wouldn't insult me if you let me know. You can definitely contact me afterwards. I have my email address, and I'll post it later, and of course my Twitter handle. And lastly, again, my self-esteem is directly linked to the number of Twitter followers I have, so please consider following me. And yeah, that's it. So using Go's rich standard library, the thing I want to talk about is Go's surprising capacity for building powerful abstractions. Again, even though it's a compiled language, we'll discuss a particular SQL access pattern that I've used. So in building the product that I'm working on, I have to do kind of a lot of repetitive SQL queries, and I found myself kind of falling into the same pattern over and over again. And what I realized is that I could do a lot simpler. And so as I go through this, if you know C or C++, please keep in mind, or keep in mind how difficult this sort of thing might be to do in those languages. So simplifying SQL queries. Here goes kind of like the bog standard way to query a database in Go. And this really isn't that bad, but here we actually execute the query, check if there's an error. And then what I do is I create a type, and I iterate over the rows and map each of the rows to a member of my employee struct. And as I build each struct, I append it to a slice, which is basically kind of consider that like a variable length array in Go. So I append these to a slice, and this isn't too bad, but if you do it over and over again, we'll notice some problems. The first, hold on one sec. I lost my notes. There you go. All right, so the first is that we have to manually map database columns to struct fields, and we also have to know the order in which the results appear. So there's two places where we have to like specify the order that the columns will appear, and then another place where we have to remember that and then actually map those columns to the struct. We have to manually append the slice, append the structs to our slice, and we have to. And if we do this a lot, we have to repeat this entire pattern often. And of course, there's a lot of the extra boilerplate kind of error handling that we have to do that we can eliminate. So can we do better? Yes. So as I've been doing this, I tried to think of how I would ultimately want to be able to kind of execute this pattern. And this is what I want. I want to be able to pass a type to a query and have it automatically populate this sort of list of results. So there's other packages that allow you to do this, like SQLX. But like a lot of things, I like to try to learn how to do stuff myself. But also, since Go has such a rich standard library and has such powerful features, it's actually not that hard to do it on my own. And one of the side effects is that eliminates kind of an external dependency to my project. So here are kind of the ingredients that I'm going to use to sort of build this abstraction. The first thing is something called method sets. I'm going to use the database SQL package. There's a feature called field tags. There's something called interfaces, a reflect package, and then the ellipsis operator. Those are, obviously there's going to be a lot more that I use, but these are kind of like the major components I'm going to put together in order to build our abstraction. So very briefly, the first thing I'm going to talk about is type method sets. So in Go, a type could have methods associated with it, and a list of methods associated with it is called method set. And so here's a brief example. I create a type called name. It's simply a string. Whoops. So I have a type called name. It's simply a string, and I have a method associated with it called capitalized. As you can see, the function declaration for capitalized has this thing right here that looks like a parameter. It actually is a parameter, and it's called a receiver value. And what I could do is, if I have an instance of that type, I could call the capitalized method by using sort of the dot operator, and that effectively passes that type to our function. But there's something extremely powerful about this, and again, coming from C, it kind of, I realize it's kind of mind-blowing, which is that a lot of times, how can I say? A lot of times functions. Well, let's take the C sort of functions that print something to the screen, like printf, or not printf, like let's say fwrite and the write function. Both of them take the first parameter, which kind of contains the details about how it's supposed to print, and then the rest is the same, right? The rest is going to be some string that you're supposed to print. Well, what receiver values do is hoist those details out of the parameter list, so that the method can only talk about exactly what you want to do without having to understand, like, the details. And this is going to come back later. But in this case, what I've done is I created a type name, and I have a capitalized method associated with it. And all it does is it uppercases the first letter in each word, and I could execute that method by doing n.capitalize, and if I run it, we'll see that it prints capital Donald, capital Duck. Okay. So those are method sets. And so Go's SQL package, Go has a built-in database API, and the beauty of this is that regardless of the database backend you use, you could use the exact same API to talk to it. The only external like package or software you might need is the database driver, which actually implements the kind of wire protocol for your database. And so in this case, I'll be using the SQL.db.query method and the SQL rows.scan methods. Oh, and also, if you don't use Postgres, you're probably doing something wrong. It's kind of just an opinion there. Field tags. So Go allows you to associate arbitrary strings to to struct fields. And again, coming from C, this is kind of mind-blowing. The types of things I could do with this, or the possibilities that this opens are pretty powerful. And so again, I could annotate struct fields with arbitrary strings and then retrieve them at runtime. So there's a little program that's kind of that's running in the background. and I just ran it, and what it did was it iterated over the fields in that struct and actually output the actual field tag. So again, you can put absolutely any string. You can, so this basically serves as kind of runtime sort of like struct documentation, and I could change this to anything. And if I rerun my program, you can see that we extracted foobar out of it. But Go provides a convention of extracting comma-separated key value pairs from these field tags. And so we'll be utilizing that. And it's also used in like standard libraries where, in this case, as you can see in my person struct, I've associated I've mapped JSON attributes to my struct fields, and also I mapped XML elements to my field struct. And again, this is a comma-separated list of key value pairs. And if I run this, I have a little program that extracts the JSON keys. And so again, all this is happening kind of at runtime. All right, so interfaces. Interfaces, again, they're kind of the foundation of abstraction in Go. An interface is actually a type that specifies a method set, which is, again, a list of sort of method signatures that the adhering type must implement, and can contain values that adhere to the interface. And so interfaces in that way can be used as a proxy for any type that adheres to the interface. And furthermore, adherence to an interface means that a type, how can I say, means that a type implements all the methods, excuse me. Yes, adherence to an interface means that a type must implement all the methods required. And a type doesn't have to declare up front that it does conform to an interface. It'll conform by simply implementing that. So I'll demonstrate that next. So here I create a simple interface called speaker, and what this shows is that it requires a type to implement the speak method that returns a string in order to adhere to this interface. And so I create a type called duck that implements speak and returns a string, and of course it'll return whatever duck you pass to it plus goes quack. And also have a struct called human, and it has a member called name, and its speak method will return human.name, says hello. And so the interesting thing here is that, or one of the interesting things here is that those are two different types. Like duck, obviously it's a type of its own, but it's simply a string, whereas a human is a struct. But here we define a function that takes an interface, and we can pass it both a human or a duck. And I mentioned before that the receiver method, or the receiver value, kind of hoists the details out of the function signature, right? So in this case, our speak function only cares whether or not our type implements a .speak method, and it doesn't care about the actual underlying type. And so here, as you can see, I can pass two different types to speak, and all speak has to do is execute the speak method again, and the interface kind of acts as kind of a proxy for the actual underlying type. And this is used a lot in kind of like Go standard library. I think a great example of it is like the IO writer, IO reader interface. This is an extremely powerful and extremely common pattern and abstraction technique in Go. And just very briefly, I just wanted to show kind of the interface details, because we're going to look at this later. But essentially, an interface, this is like literally a copy of the interface struct from the Go source. And interface consists of an itab. I don't know if you can see my mouse. Let's see. Yeah, so it consists of an itab. That's basically the method set that's associated with the interface. This runtime object is simply a pointer to the actual data, that's stored in it. And then this type struct actually stores type information about the data that's associated with it. So, is it a string? Is it a pointer? Is it a slice? The names of fields and that kind of thing. But ultimately, kind of simplified view is that an interface encodes a value, a type, and methods. Oops. And of course, I'm going to throw all that out. We're going to talk about the empty interface, and this is one of the things we're going to use in order to build our abstraction layer. The empty interface has no methods associated with it, so no methods in its method set. And so in this way, the empty interface can serve as a type that can contain any other type, right? So since there's no methods associated with it, any type will satisfy the empty interface. And so we'll be using this knowledge in our database abstraction library. And here's a brief example. So I have a function called acceptAnything, and its parameter is I, and it's an interface that has nothing in it. And I can pass it anything. So here I'm passing it a 10, and it's able to determine that the type of the value that I passed it was an int. If I change this to, for example, a string, it works all the same, and it's able to ascertain that I passed a string to it. So again, we'll be using this in the future. And finally, the reflect package. So this is where some of these concepts I talked about kind of get tied together. So the reflect package is part of the standard library. Most sort of dynamic languages implement a notion of introspection, and that's kind of the ability of the language to look in on itself and kind of see the symbols and objects and functions that exist in that language's runtime. Well, Go doesn't do that. Go does something called reflection, where when you pass a value via an interface, since in that slide I showed you earlier, the interface actually stores the actual value and then the type information. Once you store value in an interface, you can then inspect it. And so that's what the reflect package does. It provides methods for you to kind of inspect type information and value information at runtime. And so we'll dive into that. So back to that graph I showed you, the reflect type of function returns literally this substructure of the interface that contains, again, literal type information like the size, what type of type it is, the names, the fields if there are any, and that kind of thing. And the reflect.type provides methods that allow you to inspect those things at runtime. And likewise, the reflect value of function returns type information and the actual value of it. The reason we kind of need the type information to go along with the value is that, of course, the type information contains stuff like sizes and things like that, offsets into the actual memory that's pointed to. And so the reflect.value type provides methods for inspecting and even modifying values at runtime as well. So again, this is distinct from introspection, and for a compiled language and for a kind of a static language, this is extremely powerful and allows you to do things at runtime that you typically aren't able to do with compiled languages. So brief summary, reflection is Go's way of examining type information at runtime. Reflection relies on the fact that type information as well as the actual object data is stored in an interface when it's assigned. The reflect package follows interface pointers to kind of glean information about the type. And so some of the information that we'll be extracting using the reflect package are those is that arbitrary text that we associate with struct fields. Suddenly I'm drawing a blank on the name of it. If somebody wants to type it into the thing, I'm having kind of like presentation amnesia right now. But field tags, yeah. So one of the last things we're going to talk about are variable arguments and slices. So for variadic arguments in Go, the way you pass them are, I'm sorry, let me rewind. So variadic arguments in Go can be expressed as comma-separated values and function calls. So like in this, printf takes an arbitrary number, and so we execute the function by separating each of the arguments using commas. But under the hood, Go converts variadic arguments into slices. And again, slices are kind of variable length lists in Go, variable length arrays in Go. As a result, any place variadic parameters are implicitly converted to slices, slices can be supplied explicitly. And I know that's kind of a complicated sentence. Maybe a good summary is, that is, you can pass slices to functions that expect variadic arguments. So in this case, I created a function called f, and it takes an arbitrary list of words of type string. And so the ellipsis operator in the function parameters indicates that that's a variadic argument. And so I could either call f by explicitly specifying each parameter in the command or in the function call, or I could pass it a slice, and this is a literal slice of strings, and use the ellipsis operator to say expand this into the variadic parameters of the function I'm passing it to. So if I run this, as you can see, both of these functions behave identically. So that's basically it. So those are some of the things we'll be using in order to build our API. Where we will be using the variadic arguments is that the scan function, when you're scanning database rows, clearly you don't know ahead of time like how many columns you'll be reading. So the scan function takes a variable length of pointers that it'll store the results into. And so what we'll be doing is building a slice that will pass the scan that corresponds with the struct fields that we'll be mapping to. All right, so putting it all together, I hope I haven't lost you guys. I hope you know, I know I'm moving at a pretty brisk pace. I hope most of this makes sense so far. The API I want to build, the core of it is a function called Marshal, and you know, the idea is that I'll be sort of marshaling resources or marshaling or kind of gathering database columns and then kind of packing them into our slice. And the parameters for Marshal will be an empty interface because I don't know exactly what type I'll be passing. Or I'm sorry, it'll be an empty interface because I don't know exactly what type I'll be passing to it. And then an instance of SQL rows, and that's just a type that I can use to iterate over my result set. So we're going to take the building blocks we talked about and build an SQL marshaller. I want to be able to annotate our structs with fields which describe how to map SQL results to our struct fields. My function should accept a pointer to a slice of these structs and a database result set, and then append the results to the slice. The reason we use a pointer, Go is pass by value only, and so much like C or any other language that's pass by value, in order to actually modify the thing that's passed to a function, we have to pass a pointer to it. And so what we'll do is dereference that pointer and then modify that thing that we're pointing to. As you saw earlier, other packages use like JSON or XML keys to indicate how to map those things to JSON and XML. And in this case, I want to map SQL columns to our field structs. So I'm going to use the call tag or call key. And so let's start digging into the code. First, if you want to like kind of follow along, I have a version of this that is pretty heavily commented in my GitHub. If you want to download it, it's right there for you to retrieve. And so we're going to very briefly kind of go through the process of building this. So the beginning of our function declaration, our Marshal, we use a reflect value of to actually get the value of W, right? So our first parameter is W, it's an empty interface. And so reflect value of, if you remember that graph that I showed you before of the actual reflect, the actual interface struct, that value of will sort of wrap up the type information and the value information and store it and then allow me to kind of inspect it. And so I store that in my deref variable. And so the first thing I do is I ensure that the first thing I pass to my Marshal function is a pointer. And so again, the reflect package allows me to kind of inspect the type type information. So the first thing I do is test if deref.kind, and kind returns what type of variable it is. I test whether or not it's a pointer, and if it's not a pointer, then I immediately return an appropriate error. So once I've determined that I do have a pointer, the next thing I want to do is actually like get the value that that pointer points to. And I know that's a little bit that's a little bit complicated, or that might be a little bit confusing. But so the elem method does just that. It gives me an element of whatever type that a value points to. And in the case of a pointer, that effectively dereferences it. And so again, I can inspect what kind of type that is. And so what I'm expecting is that I pass a pointer of slices to, or a pointer to a slice to my function. So at this point, I should be able to check whether or not the kind of this value is a slice, and if not, again, return an appropriate error. So far, we've kind of ensured that the data that's being passed to Marshall is what we expect. So now for some optimization. I know that later I'm going to want to ask for the index of my columns by name. That is, if I do a query and the columns are, A, B, and C, I want to be able to find out what the index of column C is by asking for it by name. So the rows.column returns a list of columns, or a list of names of columns in the order that they appear. And so what this does is creates a map. This is basically kind of an associative array, or I guess in other languages called like hashes, where in this case it's indexed by string, and the value at each index is an int. And again, so I'm creating this variable called callMap, and it will allow me to access the index by name. So as the verbiage in my slide says, this loop buffers the mapping between our fields and the columns in our SQL result set. And we fetch the field tags. Well, this sentence doesn't belong there. So a little bit more optimization. We're basically doing the same thing for the actual field tags in our struct. So here I'm iterating over the fields in my struct, extracting the field tags that have the column prefix, or my call prefix. I'm testing whether or not that field tag exists in my column map. So basically, it iterates over the field, over the fields of the struct, and determines whether or not we're actually like writing any data to this field. And if not, it just continues, skips it. If it does, it kind of caches the index of that field in another map. And kind of as a sanity check, we want to make sure that the length of our field cache and the length of our columns cache is the same. And basically what that means is what this checks, or what this ensures, is whether or not we can copy all of our columns to destination struct members. One of the last steps, if you recall, we talked about how row scan expects a variadic list of empty interfaces. So we know that row scan will have to write to how can I say? We know that row scan will have to write to at least the number of columns, or exactly the number of columns, number of any empty interfaces. So here we build a slice of empty interfaces of length of our columns. So I'll just read the verbiage. Eventually, we're going to call row scan, which expects a variable number of empty interfaces that contain pointers to memory locations, into which row scan will store row data. The slice only needs enough cells to store the number of fields to map to SQL columns, which is why we limit its size to I wrote fields, which is the same as columns. We also create a new value. Oh, and forget about the slide. And so the next bit of code actually performs this mapping, right? So we iterate over our columns, find the struct field that corresponds with that column and store the address of that column, or store the address of that field in our array, or in our slice of empty interfaces. And so these illustrations are supposed to kind of show the process we're going through. So if our result set contains an ID, name, and age in that order, and our employee struct contains an ID, name, and age in that order, then it's a pretty easy, pretty direct mapping. But if the result set is a different order from our actual field, our actual struct fields, then what this loop does is ensure that we have the proper mapping of results to struct fields. And this is just another view of the same thing. I was hoping that this illustration would be more meaningful, or would help you if the last one wasn't very helpful. I don't know. I think what it really shows is I like using GraphViz, and I like making charts like this. But this shows pretty much the same information. And really, this is it. So this is kind of like the main sort of like inner loop. So we iterate over our rows by calling rows.next. Well, of course, we do a little bit of error checking if row scan. So then we call row scan, and we pass it our desc slice, which, if you remember, is a slice of empty interfaces, and I use the ellipsis operator to kind of like expand that desc slice over the parameters of scan. And of course, if it returns an error, I immediately bail out and return that error. Otherwise, I append that data to my result set. And so again, I'm also using the reflect package to do this. X is the value that of my dereference slice, and x.set is basically equivalent of equating something to that slice. So x.set reflect append my new element is effectively this if I did it in raw Go. But since I can't do that in this, since I'm using the reflect package to kind of build this type. And so what we get in the end is an API that allows me to do something like this. I can create a struct. I can annotate each of the struct fields with the corresponding column that I expect to get out of the database result. I can execute the query, obviously test if there's an error. And then in this case, I'm using the Marshall function that we just built to build that build our slice and even print the value of it. But you could take it one step further and wrap Marshall with a function that performs a query and the marshalling in one go. So as you can see, even I can build a powerful library to abstract database access. I don't know how I'm doing on time. Let's see. It looks like I'm a little bit over. If we have like, do we have 5 minutes to do live demo?
Sure. If you need a few minutes to do a quick demo here.
Let's see. I'm going to. Okay, so here we created a simple database. Again, I've been kind of beating up on this kind of employee table, and I packed it with some sample data, so we could run PSQL data model. And so just to verify, so here goes our data, where we just verified that we actually have a table with the data we expect. And here is an example of kind of our old way to do it, right? So in this case, if I have an employee struct, I have to manually iterate over the rows, but it kind of works, right? And I'll append to it and then print the resulting slice. I can just say go run, repeat, go. Let me, so name, ID, age. Okay, sorry, I got a little ahead of myself. As you can see, we successfully queried the database, packed it into a slice of structs, and here's kind of a rough dump of the data that's in memory. But the problem is, as you saw, if I change the order here, result set, it's simply not going to work, right? It's going to say that the columns don't match, or if I don't have the same number of columns, for example, it's going to say that the destination arguments don't match the number of columns. And so as you can see, there's two places now that I have to remember to kind of keep in sync. But if we include github.com and for fast flow, I can condense all of this into so this should be it. So here we're going to annotate our struct with our field tags. So I'm going to say this column maps to ID. This column maps to our name column. And this column maps to age. And if the demo gods are on my side, we should be able to run this. Of course, no new variables. Right. And so, as you can see, I eliminated a lot of boilerplate. I eliminated a lot of iteration, a lot of error checking, and I get the exact same output. But more importantly, I can eliminate, or I can change my query, and the code will kind of adapt to those changes and just try to map whatever fields are available to the existing struct, right? So now I'm only extracting one thing. I'm only extracting age. So you can see all the ages are properly populated. Or if I want to do the name, ID, and age out of order, that doesn't matter either. But again, so my purpose here wasn't to convince you to use this package. Wasn't to convince you not to use SQLX. It was to show how easy this is to do on your own, using some of the abstraction techniques that Go makes available to you out of the box. I hope, even at the pace that I went through this, that it was informative. And yeah, that's all I got. If you have any questions, I'll stick around until afterwards.
Thanks for watching.